Hi everyone, so we're the Acetones. I'm Shirley.
I'm Saud.
My name's Mike Betchik.
I'm Landon Delicio.
And I'm Ishban Aziz.
So we're here to talk about our acetone retrofitting plant.
The objective of this project was to design and build an acetone recovery unit. Our other option was to either burn it or sell it and design it. So we went with designing and building a recovery unit. The acetone can be recovered and then can be sold for into the marketplace for profit. However, our team, after feasibility and economic analysis, decided to sell acetic acid, methanol, and hydrogen as well for maximum profits. Acetone is one of the most important and simplest ketone. It is used as it's a chemical solvent. It is also used for thinning polyester resins and cleaning tools. Also, it plays a heavy role in cosmetic industry, such as nail polish removers. So our design process was consists of four main components. First is the acetone and methanol recovery from the feed stream, the waste feed stream. So we recovered acetone and methanol through PSA, pressure swing adsorption. The second was removing the acetic acid due to its corrosive nature that could lead to damage of the stainless of our pumps and tanks. The third and fourth one is the reacting of isopropanol in a shell and tube reactor, and then recovering our product acetone, methanol, and hydrogen, and recycling them back in through the various separation processes for maximum recovery.
Okay, so I will be talking about the mass balance for this process. We did a mass balance for this process, and the overall mass balance shows that we are losing about 3.4 pounds per hour. However, this is a very small percentage of our total feed, and when we do a tolerance analysis, it turned out to be 0.01%, which is within the acceptable range. It is also important to mention that when we initially attempted to do the mass balance, we have used a model that is based on the difference in the boiling point temperature. However, that model was not accurate because it does not account for the isotope that forms. So therefore, we have used the recovery numbers that we get from HYSIS. And that's basically about our mass balance.
So as Saud had said earlier, one of the main things that we have based our initial estimations and initial design on is the boil point differentials to which we can separate things effectively. Now that assumes that with the boiling point it separates at 100%. However, for the majority part of our process, it is the acetone and methanol streams have been problematic as it does form an azeotrope. Now, for us to combat this, we have used a pressure swing operation to which one of our extractive distillation columns is running at a higher pressure, for instance, 175 psi, and our distillate stream is going to a second column, which is running at a lower pressure. For in our case, it is around atmospheric pressure, and then this gets recycled, and we get a very pure product in the end. Now, another thing that we have also done, which is also a design variable, is the use of a vacuum distillation. Now, in the vacuum distillation, it is able to separate out acetone and methanol in one go. However, one of the biggest problems with this is that we need a lot of money to maintain this vacuum for it to continually running, meaning that our utility cost is going to go way up. And for this may not be viable, especially in the long run, and also with the maintenance and the operation of this may not even be viable, say 5-10 years into the future. So we've decided that while that is a viable option, it isn't the best option for us.
Okay, so I'll be talking now about the reactor key variables. So the first thing to understand our reactor is to understand the reactions that are going in our process. The reactions that are going into our process is a dehydrogenation reaction of alcohol, and more specifically dehydrogenation of isopropanol, which is going to give us acetone as our main product, and methyl oxide and propylene as our side product. Also, we are experiencing also methanol is going to undergo a dehydrogenation reaction in which it's going to yield formaldehyde. So it is important to remember that these reactions are equilibrium reactions, meaning that they're going to follow Le Chatelier principle. And in order to make the products, or in order to ship the equilibrium towards the products, we need to keep three things maintained. First of all, we need to operate at low pressure in order to favor the equilibrium. Second, operate at high pressure. And the third thing is to make sure that the products is continuously being removed from the outlet of the reactor. That's about our reactions. Now we want to pick a temperature and a WHSV, which is basically represent the amount of catalyst that we're going to use in our process. That's gonna maximize our conversion and selectivity. So in order to do this, we have done a knee analysis, and this was done by plotting our selectivity versus the conversion. And the knee region as can be seen here, occurs between 550 Fahrenheit to 650 Fahrenheit. So our team has decided to go with a 550 Fahrenheit. Now that we know that the optimal temperature is 550 Fahrenheit, or what we have chosen, which is within that limit, we need to know what is the optimal WHSV, or in other words, what the optimal number of catalysts that we need to maximize our conversion. And we also did an analysis for this by basically plotting the WHSV versus the conversion. And as we can see that the knee region occurs at a WHSV of 0.25. So that's why we have picked a temperature of 550 and a WHSV of 0.25. So in the end, we have chosen a shell and tube reactor, and this is mainly because two things. The shell and tube reactor is a continuous reactor, which means that it's gonna continuously remove the product at the outlet. And the second thing is that through a shell and tube reactor, you can actually control the temperature, which is very important because the reactions, the nature of our reactions are endothermic, and this means that they're gonna give off heat. So we have to supply this with a hot oil in order to keep the temperature across the reactor nearly isothermal, so that our conversions and selectivities are not affected.
Next, we have to look at the utilities for our plant. Obviously, running such a large chemical plant will require a lot of utilities. Here we have a table of all the utilities we have available to us, mostly different pressures of steam, cooling water, power, and downtherm hot oil. We maximize the cost-benefit analysis of this by choosing the appropriate, the lowest possible cost of the utility for each process. Some require a high temperature, so they need high pressure steam, but however some could be only require a little bit of energy input, so we could suffice with low pressure steam. Special consideration had to be taken for the reactor since it operates at such a high temperature. At 550 degrees Fahrenheit, the only utility we have that could reach that temperature is downtherm hot oil. This is obviously the most expensive cost at $22 per MMBTU. However, we must use this in order to maintain the endothermic reaction going on. We experienced only a temperature drop of 10 degrees throughout the reactor, so we did a cost analysis on the total amount of dollars it would cost per hour to maintain that, and it came out to around $58. A further analysis was done on the total cost of all utilities in the plant, and we found that to be just under $1,100 an hour.
All right, so next we had to look at our outside battery limits. We had to look at all the things that wasn't directly calculating for cost within our design process. So in order to do this, we had to use similar bids from other plant designs. So what we did is we looked at site development, utilities for both the cooling tower upgrade as well as the boiler system upgrade, raw material and product storage, and environmental factors that will attribute to costs. So what we did is we took bids from old estimates from previous years, and we took the capacities of which those bids were estimated at, and we plugged it into this equation that calculates for all those different things for escalation, as well as for the ratio of the capacities. And we use that to find our overall outside battery limits for each of these different specifications. And this is what we had came up with. So our adjusted costs in thousands for all of the above is, you can see over there to the right, that's highlighted in yellow.
The total capital cost of this plant is $57 million. We plan on building the plant in a total of 3 years. The first year we'll use 15% of the total capital cost. The second year we'll use 35%, and the remaining 50% we'll put toward the third year. As you can see from this pie chart, the OBL and IBL dominate most of the capital costs. All the IBL costs were found using Aspen Process Economic Evaluator, which gave us a detailed list of all the equipment and the prices with a bunch of factors so we can ensure an accurate number. The OBL, as Landon mentioned, was calculated with a correction formula. We also had to include contingency in our economic analysis because no project ever is perfect. We expect at least some construction delays or price increases or decreases, so we wanted to have a buffer in order to maintain a consistent budget. Escalation was also included in this because the plant is being built over 3 years, so we must take a little bit of inflation into account since $1 today is not worth the same as $1 tomorrow. Utilities and overhead will be the most expensive fixed costs we will incur while running the plant. As you can see from this pie chart, utilities dominate 65% of the total fixed cost, and employees and administration take up 31%. We made one giant assumption here that the feed we are getting to run our entire retrofit plant is free. We made this assumption because we already own the other plant and these are waste streams coming in. Now we were presented with 3 options before this plant, either sell it to Wasteco, burn it, or build a retrofit plant. And we found that the best one would be to build the retrofit plant because of all these economic factors. Also a little bit of security and administration fees must be accounted for in there also. But as I said, the feed is assumed to be free, and we cannot, because we already own it, we don't want to pay for something we already own. The total proposed plant will be profitable. We have found that at the current market price of 73 cents per pound of acetone, we have an after-tax rate of return of 24%. This is actually a pretty decent number for a project of this scale. We also found a net present worth of $44.1 million. After conducting some research, we have found that general guidelines for a successful project lie in the range of greater than $30 million of net present worth and over 20% of after-tax rate of return. So we meet both these criteria, and we recommend moving forward with the project.
So in order for us to test our sensitivity of our model, we have changed a few things so that we can account for this. So one of the few things that we have to change is the price of acetone and the price of electricity. Now, should electricity costs go up, the annual rate of return will go down, and if the acetone price does go up, which is great for us, the annual rate of return is going to go up as well. Additionally, we should also take into account of what happens if we do end up having a surplus. Now, if we do have a surplus, for instance, like a 8%, a 10% surplus, our annual rate of return is actually going to go down. And additionally, we've also done another analysis, which is if we were to run a plant capacity that is lower than 100, and through this we found that if we run it at a lower capacity, we've done it at 90%, our annual rate of return is under 10%, so that isn't good.
Lastly, since this is a capital estimate project that we are doing here, we wanted to do a PDRI, which is a project definition rating index, on our project here in order to assure confidence for our investors. That way they know going into this that they can have trust that we've gone through all factors within the front end planning process in order to build confidence in their investment. So through each gate, we'd go through and do a PDRI, and you can see with after gate 3, which after we'd focused on all of our mass balances and we'd finalized our actual design, we had a PDR rating that was in the typical limits between the min and max there. And as we moved forward into gate 4 and we started doing sizing, there was a lot more factors that we had to look at, a lot more of the elements within the PRI that had to be taken into account. And we started to fall off track just a little bit, so we knew that we'd have to go through and really double check all of our different planning factors and increase that rate. So as we moved into Gate 5 and we had an overall detailed scope of our project, we got back into the required limits. That way you can be sure that we've gone through and double checked that we have a process that is worth investing in.
So in conclusion, we were presented with a challenge. We had 2 waste streams coming out of our existing acetone plant, and we had 3 options from this. 1 was to sell direct to wasteco, 2 was to use the streams as fuel to lower utility costs, and 3 was to build an acetone recovery plant, which we recommend on doing. After our cash flow model, we found that our net present worth currently is $44.1 million, and our after-tax rate of return is 24%. These fall within the guidelines of a proposed successful project, so we recommend building the plan. Thank you.